Buff here again. Let me begin this video with a suggestion. All of you students out there, every time you see a square, I want you to think of the number, the square root of 2. Whether it's floor tiles, a baseball diamond, any square you can imagine. The square root of 2 is a really strange number which is intimately tied up with every square. And let's explore that a little bit. Let's start with a square where each side is 1 unit long. We'll think of this as 1 foot, and then we're going to be talking about a baseball diamond. So we'll imagine that this square is 90, each side of the square is 90 feet. That'll make it a baseball diamond. And we're talking about a dilation factor of 90 here, which obviously I couldn't draw very well. So I'm asking you to pretend that we're going to dilate this square where each side is 1 unit to a square where each side is 90 units. Well, if you have a square where each side is 1 unit, the length of the diagonal is the square root of 2, and that comes from the Pythagorean theorem. We have a right angle here, so we have 2 legs of the right triangle, either these 2 or the other 2 over there. And we know from the Pythagorean theorem that when you square each of the legs and add those squares together, that'll exactly equal the square on the hypotenuse, which is always represented by the letter C. A squared plus B squared equals C squared, the Pythagorean theorem. Well, when you work this out, 1 plus 1 equals C squared, 2 equals C squared. So the C, which is the diagonal of the square, is whatever number you can square to get 2. And the number that you can square to get 2 is what we mean by the square root of 2. So if C squared is 2, C is equal to the square root of 2. The square root of 2 is irrational. It cannot be represented as a fraction. Very strange thing. But the point of this lesson is that it's not just a square where each side is 1 unit long that has the square root of 2 associated with it. It's any square, no matter how long each side is. So let's consider the baseball diamond. It's called a diamond because of the perspective. If I tilt my head like this, I can consider this to be home plate, and that's second base, first here, and third there. So we're going to consider the question, how far is it from home plate to second base? That would be the same as the distance from first to third. It's the diagonal of a square that is where each side is 90 feet. That's the distance from home to second. Back to the dilation. If we dilate, and again, we're pretending because this is nowhere near a 90 times dilation of this square. But if we realize that in this square, the diagonal is also a line segment that is getting dilated. If we're going to dilate each of these sides times 90, then the diagonal would dilate by that factor as well. So it's a very simple matter looked at from the point of view of a dilation. The diagonal of a square where each side is 1 unit is the square root of 2. The diagonal of a square where each side is 90 units, 90 times the 1, is going to be 90 times the square root of 2. It's going to be 90 times longer. Very simple. But this allows us to bring in a skill that I don't think it's too early to learn in 7th grade. It's something you definitely need once you reach Algebra 1, once you reach high school math. The skill that I'd like to introduce you to now is called simplifying a root. Let me give you a quick example with smaller numbers. The square root of 20 is the number that you multiply by itself or square to get 20. And of course, it's somewhere between 4 and 5, right? It is less than 5 and greater than 4. And just like the square root of 2, it is irrational. It's not a fraction. You can approximate it to many digits with a calculator, but it's irrational. But here's another thing we can do with the square root of 20. We have a rule in math regarding roots that, put into words, you could say it like this. The square root of a product is the same as the product of the square roots. So if we think of the square root of 20 as the square root of 4 times 5, the rule tells us that the square root of 4 times 5 is the same as the square root of 4 times the square root of 5. The square root of 4 is 2. The whole number 2 times the square root of 5. These two numbers are both irrational. This is still an irrational number. When you multiply the square root of 5, which is irrational, by 2, it's irrational. But it's exactly the same as the square root of 20. And the reason for that is we can demonstrate that by squaring each of them. If we take the square root of 20 and square it, and then take 2 times the square root of 5 and square that. Well, the square root of 20 squared, you don't have to worry about the fact that it's irrational. Don't think about doing a decimal multiplication. The square root of 20 squared is by definition 20, because the square root of 20 is the number that when you square it, you get 20. So this is 20 by definition. Over here, when we square 2 times the square root of 5, we're going to have 2 times the square root of 5 times 2 times the square root of 5. These two, again, by the definition of square root, the square root of 5 times the square root of 5 is 5. We have 2 times 2, 2 times 2 times 5, so we have 20 equals 20. That's a quick explanation of why this rule works. So coming back to our question about how far is it from home plate to second base, we've already seen an answer based on dilation, that this is 90 times, this is a 90-time dilation of the unit square. So the diagonal is 90 times the square root of 2. But what if we applied the Pythagorean theorem to the baseball diamond? We have A, B, and C. 90 squared plus 90 squared equals C squared. I'm going to pretend we don't know for the moment how long the diagonal is. 90 squared is 8100. So we have 8100 plus 8100 equals C squared. These two add to 16,200 equals C squared. So the answer, the diagonal of this square, is the number that you multiply by itself, or the number that you square to get 16,200. And that's exactly what we mean by the square root of 16,200. So if C squared is 16,200, C is the square root of 16,200. And that seems a little bit intimidating. But if you remember that back here when we squared 90, we got 8100. 8100 is a perfect square. So if we think of the square root of 16,200 as the square root of 8100 times 2, we can then take the square root of the product and write it as the product of square roots, so that we get C equals the square root of 8100 times the square root of 2. And the square root of 8100 is, of course, 90. So we get that the hypotenuse of the right triangle, or the diagonal of the square, is 90 times the square root of 2, which is, of course, what we knew it was based on the dilation. So just to sort of round out this lesson about the distance from home plate to second base in terms of the Pythagorean theorem and the square root of 2, I looked up on a website, asked the question, how far is it from home plate to second base? And I was given this answer: 100 127 feet, 3 3/8 inches. That's what the website told me. It said specifically that that's measured from the back point of home plate to second base. I'm not sure what part of second base, of course. We have the advantage in geometry of everything being perfect. Things aren't perfect out in the real world, but this comes out to be very close. It's a nice result because I'll use a calculator here. I'll take the 90 times the square root of 2. See what I get for that. Using the calculator, typing in, finding the square root of 2, and then multiplying by 90, I get a result that I'll round to the nearest hundredth. I got 127.28. 127.28 is an approximation for 90 automatic lights. Love them. Not everything that can be invented should be invented. Never been a big fan of the automatic lights. Just shut them off when you leave. Anyway, 127.28 feet. If we take 0.28 and multiply it by 12 inches in a foot, 0.28 times 12 is 3.36. This is 3.36. So that'd be equivalent to the inches. And 3 3/8 inches, of course, is 3.375. But this is pretty close. 3.375, 3.36. This measurement is probably to the nearest eighth of an inch. So I think it's safe to say that we've confirmed this piece of information that I got on the web with the Pythagorean Theorem. Remember this, whenever you see a square, the square root of 2 is intimately associated with that square. Whatever the length of the side of one side of the square is, multiply that by the square root of 2, and that is the length of the diagonal of the square. So bye-bye for now. Stay healthy.